It's my pleasure to introduce Professor Michel Boufadel, who is an environmental engineer and director of the Center of Natural Resources. He is a professional engineer in New Jersey, a board-certified environmental engineer in the USA. He has served on 5 different National Research Council committees in relations to oil spills. He also served on a committee by the Royal Society of Canada on the impact and behavior of oil in aquatic environments, and served on the Environmental Protection Agency Science Advisory Board to extract shale formations. He's the editor-in-chief in Marine Pollution. So we're lucky to have him here. Take it away.
Thank you, Mohammed. I have interacted with the researcher in the Erasmus, named Mohammed Iskandarani, and Michel Ozgokmen, and there's also NJIT here. Michel was leading the consortium, and we were managing. And I see also Claire Paris, also we different group, but we also interacted over the years. So I would like to thank various people that I collaborated with over the years. Some of them are, they are listed here. They include people in academia, industry, and government. So this one. Okay. So let's talk about what happened to oil droplets in the water. So if you have an oil droplet in the water column, what we know that what happens is that you have these mixing and eddies in the water column, and then they go and kind of bombard and punch the droplet, and then they break it into small droplets. It is very important to know the size of the oil droplet in the environment or in the water, because large droplets, they rise to the surface, small ones, they can be carried away. So that determines the trajectory and then the pathway for droplets. Also, the smaller the droplet, the more likely for it to dissolve or to even biodegrade. It means get eaten by microorganisms. So knowing the droplet size distribution is very important. Another mechanism that droplets could break is when you add chemicals known as dispersant or surfactants. They reduce the interfacial tension between the oil droplet and water, and then the oil can slough off of the droplet, as you can see here. So I mentioned this because there's a lot of talk about dispersants. So the mechanism that happens due to dispersant is if you have many of them, and then they occupy the oil droplet, one side, but the tail is like water because hydrophilic, the other one is hydrophobic, so it likes the oil. And then if the droplet is moving, then these dispersant molecules, they can move to one side and then reduce tremendously the surface tension that is keeping the oil droplet together, and then you get this sloughing off. So that's another mechanism that where oil droplet can break into small droplets. I want to show this as an illustration. You can see in the top one, this is in a flask, and then we are just moving with the flask. So you can see in the top one there was no dispersant, and then you can see droplet forming. Whereas in the bottom one, you will see this mechanism that we call tip streaming, and then the oil slough off and it's forming like clouds. So that is very important to understand that. So the dispersant not only result in smaller droplets, they also generate a large proportion of very small droplet, micron-sized droplet. Now, 100 micron is the thickness of a hair. So you could imagine how small is 1 micron. Okay, here, again, today is an expose. I wasn't trying to dig very deep based on the broad background of the audience. So this is an experiment that we conducted in the Department of Fisheries and Oceans wave tank in Canada. The wave tank is 16 meters long. This one's 32 meters long. It was 16 and then later 32. And then the water depth is 1.5 meter, so 6 feet. And then the width of the tank is 2 feet, 0.6 meter. So we have the wave maker is this side, a flap type, and then creates waves. And then we put oil on the water surface, and then as the waves they get here, we lift the oil was in the ring, you will see it next, and then the wave crashes on it, and then we measure the droplet size distribution. So you can see pictures here, looking upstream, and then the wave is coming. We use a technique known as dispersive focusing, so we concentrate the waves to break in the middle of the tank. And you can see more of them here. This is looking downstream. This is the camera that we used to measure. It was made by a group affiliated with the University of Miami. And so the camera is slanted, and then the oil goes in between, and then we can measure the oil droplet size distribution. This is here looking upstream from underwater. So the wave, this is now the wave broke, and now the oil is like maybe 3 feet or 1 meter upstream, and then there's another breaker coming up. GoPro camera, that's not the shutter graph, and you can see essentially what happened based on the breakup of waves. So we measured the oil droplet size distribution and the bubbles. We found them to be approximately Gaussian, and for this case, the mean diameter was 1.2 millimeter, and the droplet size distribution was kind of tight between 0 micron and up to 2,300 micron, which is 2.3 millimeter. We also plotted the data as number as function of diameter, and then we retrieved what people call the Delvine and Sweeney correlation. People observe in the literature that if you plot the number of droplets as function of the diameter, you have a power law, and some people thought of it as that really some kind of scaling law similar to fractal. I don't think so. I think simply if the distribution is Gaussian, and then you look at the left tail, when you plot it, you log, it will give you this behavior. And then we demonstrated it here. So if you take Gaussian distribution, you take the logarithm, then you realize that it's going to rise. The left limb is going to rise d to the power 0.72. When you divide by the volume, which is d to the minus 3, then you obtain d to the power minus 2.2, which is this is what was important. So there is no scaling law. This is simply an artifact of the Gaussian distribution, the left limb. Now I reported some numerical simulation results. There were famous studies conducted by Rapp and Melville in the 90s. They had nothing to do with oil, but they did the method of dispersive focusing. So we tried to simulate, to reproduce that using grants with K omega. We understand there are limitations of using grants, but that was the first cut approach. And visually you could see that the model was able to reproduce the water surface. This is the velocity at the few locations, and again we were able to, these two locations, and we were able to approximate, to match observation. So the goal here to say is, from an engineering point of view, the model is able to reproduce observation, and then we can use it to reproduce major properties for us, like horizontal velocities, eddy viscosity, and the energy dissipation rate. The energy dissipation rate is important because it is that energy that we use to break the droplets. So you can see that the energy dissipation rate is highest at the water surface, and then it will decrease rapidly with time. By contrast, the eddy viscosity, which tells you how things spread in the water column, actually keeps increasing with time. So that means that once you have a breakup, then you will no longer generate smaller droplet, but still you will have small droplet diffusing in the water column. We also solve these equations, essentially how to move the oil droplets. So we solve the hydrodynamic equation, we get the velocity, the diffusion coefficient or eddy viscosity, and we get the energy dissipation rate, and then we use them to predict, actually. In this moment, we just track the movement. Next one is going to be about rate. So I want to illustrate here something that is important. Again, the investigation is at the meter scale. you could see once things start moving that the mass of the droplets plays an important role in where they go. So these are not passive scalar. Okay, you can see that the large droplets, which are at the bottom, they move the most outward, and that is telling us that actually, look at the density of the yellow one here. These are 100 micron, 600 micron. They are here. So that tells us that we cannot just use droplet as passive scalar. They just move by water. They have, because of their inertia, they can move actually faster. Essentially, when you hit something that is heavy, when it moves, it's not going to slow down as fast. And then now we're going to investigate the breakup of the droplets. So we use this model we call V-drop, and essentially it allows for droplet to break up into smaller droplets, but also allows for coalescence of smaller droplets into larger ones. And we call it V-drop because it accounts for situations. We apply dispersants. The interfacial tension that keeps the droplet together becomes small, but then the oil viscosity becomes the main resisting force. So that's why we call it V-drop. So now we're going to couple this model with the transport model, which is already coupled with the hydrodynamic model. So we move the droplet, and then we allow them to break using V-drop, and then we move them next and again and again. So this is a case here where we are allowing now for the breakup of the droplet. And again, this is our focus. The engineering is to try to reproduce observation. So you can see the color, the lighter one, the yellow, maybe you don't see the blue as well, but the yellow one, you can see they go deeper, whereas the red droplet, if you can see them on your screen, they stay closer to the water surface. That makes sense. The larger droplets, they like to stay, due to their buoyancy, they stay near the water surface. And we investigated different mechanisms. We consider a situation where you have dispersant, and these they made small droplets. So if they are dispersant, like this column here, and compare these column 2 to column 3. These are 100 micron, 300 micron, 400, 600. So these two columns, they have the same constant for the model, except the interfacial tension here is smaller. It needs to represent the application of dispersant. And you can see when you apply dispersant, there is a large number of smaller droplets, 100 micron, but small number of larger droplets. So, again, this is the case where we're trying to capture what is observed. You apply dispersant in a wave situation, and then you obtain smaller droplets. Now we move to jets and plumes, underwater. And essentially, so as you have blowout, the oil comes out, and then there are Kevin Helmholtz instabilities that form, and then the water is being entrained inside of, it's entrained with the oil. So like within maybe 10 diameters, you could have 90% of the volume is going to be water, and only 10% is oil. So it is pretty vigorous mixing. And then in the process, essentially what happens is that you have oil, they start shearing, oil droplet, they shear. This is an investigation from a diameter pipe. It is 1 inch, so it is 2.5 centimeter. And you can track certain features, and then you can see them. They shoot up, but then they get re-entrained into the plume. So we think this area here is a major place for the formation of droplets, and we are trying to better understand it. Again, remember this is 1 inch pipe diameter. So to follow that investigation here, we investigated the release of oil from 1 centimeter diameter pipe. And you can see here what detachment, these are Kevin Helmholtz instabilities, and you can see them forming here, like the water shoots inside and then kind of wanna uproot oil, but then because of the general motion is to suck the water towards the plume, then they reconverge. what we were able to reproduce the observed behavior, so we believe that it is the shear there that is causing the formation of the droplet and not, the pressure, as I said earlier on. So we continue the investigation in this area. This is here a simulation. On the left is observation, on the right is our simulation. It is what we call high fidelity, so spacing is about 10 micron. Remember, 100 micron thickness of a hair. For this one, we use about 60 million cells, and to get the simulation, it took about a month of simulations. And we also try to understand, what they call them the hairpin vortices based on two criteria and the oil volume fraction. And then we focus in our papers on the different nodules and different ligaments and how they break. And really, we understood the relation between pressure, shear, and viscosity and interfacial tension. I'm going to skip this and then move to this one. This is Deepwater Horizon spill. The diameter is 0.5 meter, so it's 20 inches. You can see the discoloration. Some people say this is hydrate, other people say this is gas coming out. Different opinions. But you can see it's like very puffy, it's not coming out smoothly, it is very violent. And this is something that Michel Ozgokmen actually alerted us to years back. So this paper we published in 2018. So until that time, we were all looking at, okay, you have the oil coming out, and this was the conventional kind of wisdom. That you have the oil and then the gas, and then they come out and they co-flow together. The oil rises, the gas flows with it. They are all lighter than water, so of course they're gonna go together up. And everyone was focused on what happened once they get into the water. But then we said, okay, let's look what in reality happens. So what if you go and measure, we use measurement of the gas content, and say, let's try to simulate this situation. And now, as you can see, I have to say, the orange is the oil, and then the silver is the gas. Both cases. And you can see here that the gas and the oil now, they are tumbling in the water, in the pipe. They are no longer co-flowing, okay? This flow regime is known as churn flow. And until we published it, it was not known about the Deepwater Horizon. It did people use it in nuclear engineering and in some chemical engineering application. But that was a major finding, and that it impacts how you estimate the flow rate in the pipe. Because if you use certain formulations without accounting for the tumbling, you're going to overestimate the amount of oil that is coming out. Okay, so, and again, this thing of churn flow, it's not like we are pretty certain of it based on the measurement, the chemical measurement conducted by other groups. We know that the regime is churn flow. The volume of gas has to decrease by 4-fold for the flow not to be churned. So we are pretty confident that Deepwater Horizon was churn flow. And we also developed a model that generates droplet size distribution and bubbles from blowout. We call it the drop J. I want to report some experiment here. Still have time. Okay. These are some experiments we conducted underwater at the Onset facility in Leonardo, New Jersey. That's a Navy base in New Jersey. The tank is 200 meter long, 20 meter wide, and 2.5 meter deep. We have this, we release oil here, and then we track it with instrument, shadowgraph camera, acoustic Doppler velocimeter, an instrument called LIST that also measures droplets, and fluorescent. And then we try to understand, the droplet size distribution. Now remember, the cross flow occurs at sea, because sea, you could have currents. Of course, it occurs at rivers, in tidal channels, and in different tanks. So kept constant, and then we are measuring the oil droplet size distribution and then the velocity. One thing we notice also here is that because of the cross flow, surface breakup is really different than if it is only vertical. You know, there's a lot of things that are sloughing out from this downstream end here. So the oil shoots, the current, you know, arrives there, and then the oil is going, and then it starts like sloughing things around it. These are also other features. These are simulated results. And then when you couple with the droplet, you can see that the large droplets, they rise, of course, faster than small ones. The red ones are the large ones, 3 millimeter, and then the small ones are blue, so they move with the current more. And then you could also have an issue here with, there are what's called counter-rotating vortices, and this is looking downstream, and these, they tend to trap oil droplets in them. So we can no longer assume that when the flow goes sideways that everything is mixed. In reality, no. You have like zones where things get trapped. This is more illustration here. So here we release droplets that are, you know, the red one are 800 micron, and then the blue ones are 400 micron, and then you can see the red and the, you know, larger one they leave, whereas the small one they get trapped inside of these vortices. So it is very important because the deep oil horizon people assume that, you know, you have the oil move sideways and then the droplets start leaving based on their buoyancy. Well, that's not true. The small ones, they're gonna be trapped by the counter-rotating vortices. Okay, now we're gonna get to the last part of the presentation. What happens when the oil gets to the beach? We know that 11 people were killed, 1,000 kilometers of shoreline polluted, and my team, we were tasked to investigate the persistence of oil. We were tasked by the Coast Guard to investigate the persistence of oil on the 3 beaches. One was in Grand Isle, in Louisiana, and you know, and one was in Bon Secours, Alabama, and Fort Pickens, Florida. I'm going to talk more about Bon Secours and Fort Pickens, because the one in Louisiana, actually, it was kind of swampy area, and we didn't think the oil would biodegrade at all. So this here is, I believe, is in Bon Secours. So we had these transects to measure water property, air property. We took also sediment samples. You can see the oil here. This is, so you have an oil layer. The oil did not sink in. No, it was brought in by, you know, say a hurricane, and then it was, you know, covered by another, you know, wave of sand. So there was no sinking in of the oil. It was just a simple accretion of sand on the top of existing oil. And so you can see the oil layer here or here. And so we measure, if this is the sea, and this is going landward, okay, this is in the supratidal zone. So it's like high tide and then more landward. At some locations, you know, about 11 centimeter deep, we were able, you know, we measured like very high concentration of oil, and nothing much around it. It is like where you saw that lake. Now the question is like, well, how long would it take for this oil to biodegrade? There were people investigated this, and they said, you know, look, because it is in the supratidal zone, the oil, you know, is not going to biodegrade because the soil moisture is very small. Well, we did measure soil moisture, but we measure other things also, namely salinity, nutrient concentration, oxygen. We found that there's plenty of oxygen in the unsaturated zone. Above the water table, there's plenty of oxygen, of course, connected to the atmosphere. The moisture is like 20%. 20% is not really too low for biodegradation. The heap of compost in the backyard would be operating at 20% moisture. We believe that it is actually that the high salinity, which is here about 200 grams per liter, seawater salinity is 30 grams per liter, that prevented the biodegradation of oil. The nutrient concentration is good, is decent, 10, 15 milligrams per liter, usually need 1 or 2 milligrams per liter. So everything we believe that is conducive for biodegradation except the high salinity. And so you say, okay, so what does it tell you? Well, what that means is like if you go to a beach with a suprathermal zone and then you want the oil to biodegrade, maybe you just go and pump seawater on it. Reduce the salinity, and then you enhance the biodegradation of the oil. Now, we conducted experiments in the lab, and again, I'm going to zoom a little bit through this. The first part was different salinity, but in open water, so it was in flasks. And we have 3 salinity values, 30 grams per liter, which is seawater salinity, 90 grams, 160 grams. And you can see the biodegradation here, rate or percentage. When it is 30 grams per salt, you can see that the biodegradation actually could be within 80 days, it's like 100%. 90 grams is 50%, and then 160 grams of salt is 25%. And then we can also talk about the composition, but the most important thing here is that salinity, I mean, people know that, but we just, as an engineer, I just need to quantify. So we found that actually it is the high salinity that is playing a major role. And then we conducted more experiments in a flask, in sand columns. We put sand within 6.5 centimeter in glass beads above them and below, but here it's sand, and then we mixed it with oil at 1 milliliter per kilogram. We did control, and then in some cases also we put all the oil within that one blob in the middle because to investigate mass transfer. The conclusion was, again, it is that as you move towards high salinity, you observe that there is much less biodegradation concept. We also consider without adding nutrient and with adding nutrients. And let me show you this one. This one, yeah. So let's look at this one. So this is the percent remaining. The top one this is controlled, because of potential evaporation. So that's why we conducted. That's sterile control. So we killed everything. We know that they are not disappearing by biodegradation. And then you have the case of the seawater. Hollow circle, and then you can see that remaining is like that. This is in the sand now, not in the open water. You can see that it is a lot of biodegradation, and then you start realizing that as you increase the salinity, you have less and less biodegradation. But again, this is over. This is in the sand, and then the oil was kind of spread all over the sand. So in conclusion is that we believe the salinity, high salinity in the suprathermal zone of beaches hindered the biodegradation of oil. And I'm going to stop here. Thank you.
So in your graph, it shows that it slows it down. Does it stop after 80 days, or just it takes longer for it to degrade?
Yes, it doesn't. I don't think it really stops. It just
takes longer.
Essentially, the microorganisms, they spend more energy than trying to protect themselves than to grow. And that's why they don't eat as much. You don't kill them in isolation. They just put more energy into survival.
Any other questions for Michel?
I thought Claire had the hand up there, but she turned it off again.
I have a question, Michel, about the experiment with the churn flow and the jet with the cross flow. have you been able to estimate the DSD, the droplet size distribution for the Deepwater Horizon based on these findings? And my second question would be, you know, like, what is the role of dispersant in those cases?
Yeah, that's an excellent question. Where we are in this process, we have estimated the droplet size distribution without considering channel flow at this moment. So our investigation was before. I think it would be worthwhile to pursue it, but there are challenges for us to model that. You know, so when we say, you know, if we were able to investigate it, like this week we're going to conduct experiment. Next week we're conducting experiments of churn flow from a 1 centimeter diameter pipe with dispersant and without dispersant, and then, you know, I could better understand the role of, you know, gas, you know, and how it impacts the effectiveness of dispersant, because the dispersant, you know, likes surfaces, so it likes to go to the water oil surface, but also it likes to go to the air water surface. Of course, if there's methane or natural gas, it will be, you know, more of the surfactant will be scavenged. So my answer is, it is very complicated, you know, for us to model it, to predict it. Because of that role where the gas can actually take some of the dispersant away from oil.
Thank you so much. I think you will get to that, answering that question soon, because you've done so much. I'm really enjoying to see your presentation. Thanks.
Thank you, Claire. Thank you.
So I have a few questions regarding the simulations. They're all 3D because you're looking at turbines, right?
The simulations are 3D, yes.
Including the one with the breaking waves?
Oh, no, the range simulation was 2D. Yes, correct. And yes, the range, these are, you know, the jet were, yeah, this one was 2-dimensional.
Okay.
And that's why I said it, that it is not as good as what we want it to be. Now we have what we call it, you know, large eddy simulation, LES simulations. But also those, they have their own challenges how to deal with the multi-phase.
Okay.
So, I mean, the challenge is, I think, if it is only oil and water, we are running, you know, like the paper, we just published a paper with, you know, Tamei in Journal of Fluid Mechanics, and it was LES 3D and, you know, and oil and water. But I think once there is a surface, you know, like 3-phase, then it becomes problematic for it.
Yeah, the free surface is very challenging.
I mean, for LES to be reliable, you know, like, because you're going to average equations, and then, you know, at the end you see many people use like things to, you know, to dampen the effect near the surface if you have 3-phase.
Okay. So this is Navier-Stokes solutions, not Laplace type solutions.
Correct. These are, yes, not like potential flow theory or something. Correct.
So Michel, I noticed this laboratory experiment you made in Canada, the breaking waves are the ones that really matter, right?
Right.
So how about wind? Because in the ocean you have wind all the time, and one can, you know, I don't know what does wind do.
Yes, I agree. We just have a paper published in Marine Pollution Bulletin. I think this breaker is really you can, because people do it because you can achieve it in the lab.
Yes.
I think in the ocean the main breaker mechanism is due to wind, and then you get these white caps. Now, the question is like, okay, is it oil on the water surface, and then the wind is causing it to break, or is it causing the water to kind of shear, and then, so if you assume the oil concentration is small, you're gonna, I would say, you know, we can use the white cap energy dissipation to predict the droplet size. And that's what we did in that recent work. So I think wind in the ocean, that is going to be the major mechanism for breaking of waves and subsequently of droplets.
Yeah, I mean, because it's never the case where you have like you are waiting, and some guy comes. I mean, it's the beach. Maybe in the beach.
That's in the beach, yes.
Yeah, the beach is very. But
Yes.
the open ocean, you know, it's like crazy, right?
Yeah. I mean, for us, to me, I
The
look at this.
beach is probably more.
Yeah, but I think this is a case where you have a wave breaking on waves, so there's no solid structure. So, but the question is this mechanism occurring at sea? Not much. I mean, it does occur. I mean,
It occurs, but
it's
there is
momentum.
also combined with wind, and
Ah.
wind is always acting on the maybe.
I'm telling you, like,
Yeah.
we did this because that was the only way, in the past to really understand what's going on. Now we are actually advocating for using the white caps for wave breaking. So which means that the oil doesn't go as deep. So you're not going to have, let's say, in the ocean a wave that is 3 meter breaking and then send the oil 10 meter down. You're not going to see that. If the wave is 3 meter, maybe the top 30 centimeter of it just get chopped by wind, and everything stays near the surface. So I agree with you. But what we can learn from this is about the role of shear and energy dissipation rate, but and to calibrate models. Eventually, you need to go to the ocean to validate it.
So the one that you can generate in the lab is just a plunging breaker.
Yes.
Other types like spilling breakers and other types.
You can generate spilling breaker in the lab also, but wind, wind is going to inject turbulence in the water column. Okay. So there is two roles. One is, I think, actually creates shear, and I think shear is going to be a major mechanism of generating droplets. And two, that turbulence actually is going to alter the diffusion in the water column.
Family.
All right. Nice work. So, is your group doing the larger dissimulations, or are you partnering with someone
No, we're doing it. We have
in-house?
We have, yes, we have. I am in the environmental, but we also recruit mechanical engineers.
Okay.
And that's what, and we collaborate with experts such as Tamil and Joe Katz, and with you, we have that project about the V-drop.
Yeah.
So we always reach out to people who are numerical. I'm very familiar with your earlier work on wave tanks and the Laplace solution.
Yeah.
I think Claire has another question there. Is it?
Yes,
Yes, I am still interested in the jet and the water plume question, and this time my question is with the return flow and all this energy. There's been an assumption that there is nucleation of gas inside the oil, and then as the oil and the gas, so it's a multi-phase droplet, and the oil and gas rises. There is degassing that creates larger droplets to rise faster. What is your take on that?
Yes, yeah. I think I'm aware of that work, and I think Claire, some of it is you were leading that groups or involved. I think gas definitely is important in terms of I think gas. The idea is the following: is that when the oil is in the pipe, it is what we call live oil. So that's the point. And so live oil, it means there is a lot of natural gas that is dissolved within the oil. Then as the oil comes out, the idea is that some of the gas actually remains trapped in oil droplets, and then it makes them rise faster. And there were also some ideas that if the release is rapid, then you can have kind of implosion. I think, in my opinion, if this is definitely something to consider. We need more investigation. Unfortunately, the only investigations we have is like from small diameter pipes. So you have an oil droplet that is being released, but and then yes, you can see it in these papers. They show that it is getting bigger and bigger, and then eventually like reduced by 10-fold the size. So that suggests that they're gonna implode and then generate very small droplets. However, for the deeper horizon, as we saw, I think it is the flow is very turbulent. So I feel like these droplets, if they were to exist, they're gonna be directly shaking, and then the gas is gonna get out of them much faster. But this is still an unknown. I mean, until we can test from large diameter at depth, I personally don't think we're going to have an answer for that.
Because in the simulations, it shows that the DSD, instead of being like just one mode, become two modal, where you have like very, very tiny droplet and very large droplets. In the simulation, when we put that into the Lagrangian scheme of, with multi-phase gas and...
Yeah, I mean, I think, again, it is possible. I know another group, RPS, they also advocate for bimodal distribution. I mean, I think when any oil droplet that breaks, it is based on thermodynamics, it prefers to break into two uneven droplets. It takes more energy to generate two equal droplets than to generate two dissimilar and asymmetric droplets. Okay, it's like if you have a big rock, and then it's easier to chip one piece of it rather than breaking it in half. So I do believe that things do become bimodal at some initially, but I think it could be that subsequent turbulence could make them more closer to unimodal. But I mean, if you have a cross flow, I think you could potentially get this segregation where you get the bimodal and then the small one get moved sideways and the large one continues. So I think all of these, there are possibilities. Unfortunately, you guys and us and Tamay, I mean, there are no data of droplet, near the wellhead that from what's coming out now.
That's right. Thanks.
Right.
Any other questions? Thanks, Michel.